Welcome to the Deep Dive. We're the show that tries to cut through the hype and get to the core of complex research, making it clear and hopefully usable.
Yeah, making it actionable.
Exactly. And today, we're diving into something really fascinating in AI. Think about this for a second. So much of the world isn't neat rows and columns,
Oh,
right?
definitely not. Think social networks, supply chains, even biological systems.
Right, or how chemicals bond together, or traffic flowing through a city. It's all interconnected. It forms these intricate webs, these graph structures.
Precisely. And that kind of data, this graph structured data, it's historically been tricky for standard machine learning.
Yeah, models that love grids, like for images or sequences, like for text, they kind of stumble when things get messy and interconnected like this, don't they?
You really do. It's like trying to understand a city by only looking at isolated building blueprints. You miss the roads, the utilities, the people moving between them. You miss the connections.
That's a great way to put it. And that brings us right to our topic, graph neural networks, or GNNs. These are really a different breed of AI, aren't they?
Absolutely. They're a branch of AI and machine learning specifically designed to understand and, crucially, make predictions on this kind of interconnected data. They finally let us make sense of these complex networks.
So our mission today for this deep dive is to really unpack GNNs. We want to get into not just what they are, but why they're so powerful.
Yeah, and how they actually work under the hood.
Mhm.
We'll look at some real-world examples, too, things you might already be using without realizing it.
And the goal here is clarity. We want you to walk away with a solid conceptual grasp, maybe even enough detail that if you're an engineer, you can start thinking about how to apply these ideas.
Sounds good. Where should we start?
Let's start right at the beginning. We say graph neural network. What does the neural network part actually do with the graph? How do they come together?
Okay, so a GNN, at its heart, is a neural network, but it's built specifically for data structured as a graph. Remember, a graph is just entities, we call them nodes. Connected by relationships, we call those edges.
Like people and friendships on Facebook or airports and flight paths?
Exactly. People are nodes, friendships are edges. Airports are nodes, flight routes are edges. The neural network part comes in because GNNs learn representations of these nodes and edges. They learn how to process these complex, often non-Euclidean structures.
Non-Euclidean, meaning they don't fit neatly onto a flat plane or a straight line, like a grid or sequence does.
Precisely. They handle the irregular, complex shapes of real-world networks.
Okay, so the graph gives us the structure. How does the GNN actually learn from all those connections? What's the mechanism?
This is the really cool part. The core idea is usually called message passing. Imagine each node in the network as having some initial information, some features.
Like a user's profile info or an atom's type.
Right. Then, in each step of the GNN, nodes essentially send messages derived from their current features across the edges to their direct neighbors.
Okay, so they're talking to their neighbors.
Exactly. And then each node receives all the messages from its neighbors and it aggregates them, combines them in some way, often with its own existing information.
Aggregates, like summing them up or averaging.
Yeah, it could be summing, averaging, maybe something more complex. We'll get into different ways later. But the key is this iterative process. Send messages, receive messages, update your own state based on those messages.
And this happens over multiple steps or layers.
Typically, yes. Multiple layers allow information to propagate further out across the graph. A node doesn't just learn from its immediate neighbors, but eventually from its neighbors' neighbors, and so on.
So it builds up a richer picture of its place in the wider network.
Exactly. It learns a representation that captures not just its own features, but also the structure of its local neighborhood and potentially even global properties of the entire graph. It's context-aware.
That makes intuitive sense. Why is this message passing approach so important? Why not just use the node features alone?
Because in so many real-world problems, the connections are the crucial information. Traditional models that ignore the graph topology, the specific pattern of connections, miss out on a huge source of signal.
Like trying to predict if someone will click an ad without knowing what their friend's like.
Perfect example. GNNs explicitly leverage that topology. They use the connections to inform the learning process. And this makes them incredibly effective for specific tasks.
Such as?
Well, things like node classification. You predict a property for each node. Is this bank transaction fraudulent? Is this protein involved in a specific disease?
Okay, classifying individual items within the network.
Right. Or link prediction. Can we predict if a new connection is likely to form? Will these two users become friends? Will this drug interact with this target protein?
Predicting future relationships makes sense for recommendations, too.
Definitely. And also graph classification. Here, you're classifying the entire graph.
Uh,
Is this molecule likely to be toxic? Does this social network exhibit community structure,
yeah.
typical of, say, political polarization?
Wow. Okay. So node, link, and graph level predictions. That's quite versatile. Can we ground this in some real world examples? You mentioned we might be interacting with them already.
Absolutely. Let's talk about drug discovery first. This is a huge one. Think about a molecule. It's a natural graph, isn't it?
How so?
Well, the atoms are the nodes. The chemical bonds between them are the edges.
Ah, I see. And you could add features, right? Like the type of atom, carbon, oxygen as node features?
Exactly. Atom type, charge, things like that, and even edge features, like is it a single bond or double bond?
Okay, so you have this molecular graph. What can a GNN do with it?
It can learn to predict the molecule's properties directly from its structure. Will it dissolve in water? Will it bind to a certain receptor? Will it kill bacteria?
And that leads to things like finding new drugs.
Precisely. The Hallicin story is probably the most famous example here. Researchers use GNNs to screen a massive library of existing chemical compounds.
Okay.
They train the GNN to predict whether a molecule would inhibit the growth of bacteria, like E. coli, and the model flagged a compound called Hallicin.
Which wasn't known as an antibiotic before.
No, it had been investigated for diabetes, I think, but its antibiotic potential was completely overlooked by traditional methods. The GNN saw something in its structure, and it turned out to be a potent, broad-spectrum antibiotic.
Wow. So the GNN literally helped discover a new antibiotic candidate just by looking at the graph structure of molecules.
It's a prime example of how GNNs can accelerate scientific discovery. It's
Okay.
really transforming parts of cheminformatics and drug development.
That's genuinely game-changing. What's another area? You mentioned something we use daily.
Yeah, navigation. Think
Yeah.
about Google Maps or similar apps. How do they estimate your arrival time, your ETA?
Hmm. I guess they look at traffic speeds, distance.
Right, but how do they combine all that information across a huge, complex road network that's constantly changing?
Okay, I see where you're going. The road network is a graph.
Exactly. Intersections are nodes, roads are edges, and you have features on those edges, road length, speed limit, current traffic speed, maybe historical traffic patterns.
So the GNN processes this constantly evolving graph of traffic.
Precisely. Google actually deployed GNNs to significantly improve their ETA predictions. They found that GNNs could model the complex dependencies, how congestion on one road affects surrounding areas much better than previous methods.
And did it make a difference?
A huge difference. They reported reductions in negative user outcomes, basically, wildly inaccurate ETAs by over 40% in cities like Sydney and Taichung after deploying GNNs.
40% fewer bad ETAs. I definitely noticed that. That's impressive.
It really is. It shows how GNNs can handle dynamic, large-scale graph data effectively.
And I bet recommendation systems are another big one, like suggesting products or content.
You got it. Recommendations are a natural fit. You have users, you have items, products, movies, pins, whatever, and you have interactions between them, purchases, ratings, clicks. That's a graph.
A bipartite graph often, users connected to items.
Yes. Or even more complex graphs involving user connections too. GNNs can learn embeddings for users and items based on this graph structure, leading to better recommendations.
Any specific examples?
Pinterest's PinSage model is a well-known one. They built a GNN to operate on their massive graph. Billions of nodes, billions of edges connecting users, pins, and boards.
Billions. How do they even compute on a graph that big?
That's where clever engineering comes in. PinSage uses techniques based on something called GraphSage. The core idea is instead of trying to aggregate messages from all of a node's neighbors, which could be thousands or millions on Pinterest, you intelligently sample a smaller subset of neighbors.
Ah, so you get an approximation of the neighborhood information without the massive computational cost.
Exactly. It allows GNNs to scale to web-size graphs. PinSage uses this to learn embeddings that capture visual and semantic similarity, powering their recommendations.
Okay, these examples, drug discovery, maps, recommendations, they really drive home the why. Now let's dig deeper into the how. What's actually going on inside a GNN layer? You mentioned message passing, but how does that translate mathematically?
Right, let's get a bit more technical. A useful analogy is to think about convolutional neural networks, CNNs, which are so dominant in computer vision.
Okay, CNNs use kernels or filters that slide across an image.
Exactly. An image is basically a grid, a very regular graph. A CNN kernel is a small matrix of learnable weights. It slides across the image, looking at a small patch of pixels, a local neighborhood at a time, and computes a feature based on that patch. It exploits the fact that the same pattern might appear anywhere.
So it captures local patterns, and because the grid is regular, the same kernel works everywhere.
Precisely. The challenge for GNNs is to generalize that idea, create an operator that acts on a node's local neighborhood, but for graphs that are irregular. Node neighborhoods can vary wildly in size and structure.
So we can't just slide a fixed size kernel around.
Nope, we need something more flexible.
So if I'm an engineer designing one of these layers, what properties am I aiming for? What makes a good GNN layer?
Good question. You want a few key things. One, efficiency. Computation and memory usage should ideally scale reasonably, maybe linearly or near linearly, with the number of nodes and edges.
Makes sense. You don't want it to blow up on large graphs.
Two, parameter sharing. Like a CNN kernel, you want a fixed number of learnable parameters, regardless of the graph size. The same layer should work on a small graph or a massive one.
Okay, so it learns general principles of neighborhood interaction.
Three, locality. The operation should primarily focus on a node's immediate neighborhood, say its direct connections, one-hop neighbors. Deeper layers can then capture wider context.
Similar to how CNNs build up complexity layer by layer.
Four, ability to handle varying neighborhood sizes and maybe assign different importance to different neighbors. Not all connections are equal.
Right. Some friends influence you more than others.
And five, inductive capability. This is crucial. The model should be able to generalize to graphs it hasn't seen during training. It should learn structural patterns, not just memorize the training graph.
That's a demanding list. How do we actually achieve this mathematically? What's the core operation?
The fundamental idea boils down to combining two things: the node's features and the graph's structure, the connections.
Okay.
Let's represent all the node features as a matrix, say H. Each row is a node, each column is a feature dimension, and let's represent the graph structure using the adjacency matrix, A. This is a matrix where AI, J is 1, if node I is connected to node J, and 0 otherwise.
Standard graph representation.
The simplest GNN-like operation might look something like this. You multiply the adjacency matrix A by the feature matrix H. What does AH do?
For each node I, it sums up the feature vectors H of all nodes J that are connected to I.
Exactly. It aggregates the features from the neighbors. Then you typically multiply this result by a learnable weight matrix, W, to transform the features, and often apply a nonlinear activation function like ReLU. So something like ReLU AHW.
Okay, that seems like a basic message passing step. Neighbors' features summed and transformed. But wait, you mentioned earlier that A only defines connections to other nodes. Does AH include the node's own features?
Ah, excellent point. Usually the standard adjacency matrix A has zeros on the diagonal, meaning nodes aren't connected to themselves. If you just use AH, a node only gets information from its neighbors, potentially losing its own original information after the transformation.
Which seems like a bad idea. You want the node to remember itself.
Definitely. So
Yeah.
a very common and important practical trick is to add self-loops to the graph before doing the aggregation. Mathematically, this is super simple. You just add the identity matrix, I, which has ones on the diagonal and zeros elsewhere, to the adjacency matrix A.
So instead of A, you use A plus I.
Precisely. Now, when you compute A plus IH, each node sums the features of its neighbors plus its own features. It's a simple tweak, but crucial for stable learning in most GNNs.
Got it. Add self-loops using A plus I. So this basic ReLU A plus I HW operation forms the foundation. Are there different variations on this theme, different ways to do the aggregation?
Absolutely. That basic operation gives rise to the first type of GNN layer we can discuss, which we could call sum pulling.
Okay, sum pulling.
Mhm.
Because it literally just sums neighbor features plus self.
Exactly. Hinu ReLU A plus I HW. Straightforward. But it has a potential practical problem.
What's that?
Imagine a node with thousands of neighbors, like a celebrity on a social network. When you sum up all their transformed features, the resulting vector in Hinu for that node can become huge in magnitude.
Ah, the scale can explode just because of the number of connections.
Right. This can make the gradients during training very large or unstable, making it hard for the model to learn effectively.
So sum pulling is simple, but potentially unstable for graphs with highly varied node degrees. How do we fix that?
The most common fix leads to our second type, mean pulling. Instead of just summing, we average.
Okay, how do you implement averaging using matrix operations?
You normalize the A plus I matrix. For each node, you divide the contribution from its neighbors and itself by its degree, the number of neighbors plus 1 for the self loop. Mathematically, you multiply A plus I by the inverse of the degree matrix. DD is a diagonal matrix with no degrees on the diagonal. So the operation becomes something like ReLU D1 A plus I HW.
So D1 handles the division by the degree for each node.
That's right. It effectively computes the mean of the features from the neighborhood, including the node itself. This prevents the scale explosion issue because you're averaging, not summing.
And this is generally more stable.
Much more stable. Mean polling is a really solid, simple baseline. It works well, especially for inductive problems where you need to generalize to new, unseen graphs.
Okay, sum polling, then mean polling for stability. You mentioned a really popular one earlier, GCN.
Yes, the Graph Convolutional Network, GCN layer, introduced by Kipps and Welling. This is probably the most cited and widely used GNN layer currently.
What's its specific innovation? Is it different from mean polling?
It uses a slightly different, more sophisticated normalization of the adjacency matrix. Instead of just D1 A plus I, it uses what's called symmetric normalization, D12 A plus I, D12.
D to the minus half power. What does that achieve?
Intuitively, it balances the influence. Mean polling, D1A, normalizes based on the receiver node's degree. Symmetric normalization considers both the sender's and receiver's degrees. It tends to work very well empirically, often slightly outperforming mean polling.
Why do you think it's so popular?
It hits a sweet spot. It's simple, computationally efficient, scalable, and performs strongly on many benchmark tasks. It became a go-to layer for many researchers and practitioners.
Okay, GCN uses that symmetric normalization. What if the edges themselves have important features, like the type of chemical bond or the strength of a connection? Sum, mean, and GCN seem focused on node features and connectivity.
Great point. That brings us to a more general framework, message passing neural networks, MPNNs.
Okay, sounds more fundamental.
It is. MPNNs define the process more explicitly. They typically have three components. One, a message function. This computes a message for each edge, potentially considering the features of the sending node, the receiving node, and any features of the edge itself. Two, an aggregation function. This takes all the incoming messages for a node from its neighbors and aggregates them, for example, some mean max. Three, an update function, or readout. This combines the aggregated message with the node's current feature vector to produce the node's new feature vector for the next layer.
So it explicitly models message creation based on sender, receiver, and edge features. That sounds much more expressive.
It is very expressive. If you have rich edge information, MPNNs are often the way to go. However, there's a potential downside.
Which is?
Computing and storing potentially complex message vectors for every single edge can become very memory intensive, especially on large, dense graphs. They can also sometimes be prone to overfitting if you don't have enough data to learn the complex message functions well.
So powerful, but potentially resource-hungry and data-hungry. Best for maybe smaller graphs with really informative edges.
That's often where they shine, yes, like in molecular graphs where bond types are critical.
Okay, we've covered summing, averaging, symmetric normalization, and explicit message passing. What about the idea of learning the importance of neighbors? GCN and mean polling treat all neighbors, after normalization, somewhat equally, right?
That's a key limitation they have. And that's exactly what graph attention networks, GATs, were designed to address.
Attention, like in Transformers.
Very much inspired by the success of attention and sequence models, yes. The core idea in GAP is, instead of using a fixed normalization, like mean or symmetric, let the model learn how important each neighbor is for updating a given node.
Just learn that.
For each edge connecting node J to node I, GAT computes an attention coefficient. Let's call it alpha. This coefficient represents the importance of node J's features to node I.
And how is alpha calculated?
It's typically calculated using a small neural network, an attention mechanism, that takes the features of node I and node J as input. This mechanism is learned during training.
So the network learns a function to decide attention scores.
Exactly. Then, these raw attention scores for all of node I's neighbors are usually normalized using a softmax function, so they sum to 1. This gives you a weighted average of neighbor features, where the weights, alpha, are learned by the model itself.
Ah, so it's like mean polling, but instead of a simple average, it's a weighted average where the weights are learned attention scores.
Precisely. This gives the model much more flexibility. It can learn to pay more attention to relevant neighbors and ignore irrelevant ones for a specific task.
That sounds really powerful. Is it as computationally expensive as MPNNs?
Generally less so than the most complex MPNNs. While it computes an attention score per edge, that score is usually just a scalar value, not a high-dimensional vector like some MPN messages. This makes it more scalable. Often, people use multi-head attention, computing several sets of attention scores in parallel and combining them. which helps stabilize training and capture different aspects of neighborhood importance.
Multi-head attention, just like in Transformers, that connection seems really strong now.
It is. In fact, you can view a transformer as a special kind of GNN operating on a fully connected graph.
Fully connected, meaning every input token, like a word, is connected to every other token.
Yes. If you think of words as nodes, a transformer uses attention as the mechanism to aggregate information from all other words, nodes. The main difference is that in text, the order matters, but a basic fully connected graph doesn't have inherent order.
So Transformers need something extra.
Right, they need those positional embeddings added to the input features to give the model information about the sequence order. GNNs operating on naturally sparse graphs often don't need explicit positional encoding because the structure itself provides context.
That's a fascinating link. It really frames Transformers within this broader graph perspective. Okay, so we've covered a good range of architectures. Let's shift gears slightly and talk about some cutting-edge research. NEC Labs America has been doing some significant work in GNNs, right? What are some of their contributions?
Yes, they've been tackling some really important practical challenges. One area is making GNNs more robust.
Robust to what? Noisy data. Attacks.
Both. Real-world graphs often have noisy or even irrelevant edges. Sometimes connections might be actively manipulated in adversarial settings like finance or security. GNN performance can degrade significantly with this noise.
So how do you make them tougher?
NEC Labs developed methods like PTDNet, which stands for Parameterized Topological Denoising Network. It sounds a mouthful, but the idea is clever. It essentially trains an auxiliary network alongside the main GNN to learn which edges are likely to be irrelevant or noisy for the task at hand. It then learns to effectively downweight or even drop those edges during the GNN's message passing.
So it learns to ignore the noise in the graph structure itself.
Exactly. Wei Cheng at NEC Labs put it nicely, saying something like, by focusing on the most relevant connections, we've been able to significantly enhance the robustness of GNNs, especially against noisy data, which is common in the real world.
That makes sense. If the model can clean up its own input graph, it should perform better. What about understanding why a GNN makes a prediction? Explainability is huge in AI now.
Absolutely critical, especially if you're using GNNs for high-stakes decisions. NEC Labs has also focused heavily on advancing explainability.
How do you explain a GNN prediction? Is it about which nodes or edges were most influential?
That's the usual approach, identifying important subgraphs or features. But a key challenge is reliably evaluating whether an explanation method is actually faithful to what the model is doing.
Right, how do you know the explanation is correct?
NEC Labs developed new ways to measure this fidelity, using ideas from information theory. They've worked on creating robust metrics to ensure that when an explanation method highlights certain parts of the graph, those parts are genuinely driving the GNN's prediction. Haifeng Chen at NEC Labs emphasized their goal is to make GNNs not just powerful, but also transparent and trustworthy.
Trustworthy is the key word there. Okay, robustness, explainability. What about graphs that change over time, like social networks or communication networks?
That's another area, anomaly detection in dynamic graphs. Networks aren't static, they evolve. New connections form, old ones break. Detecting unusual changes can be critical for things like network intrusion detection or identifying emerging fraudulent patterns.
Standard GNNs might struggle with the time aspect, right?
They often process static snapshots. So NEC Labs developed STR-GNN structural temporal graph neural networks. These models are specifically designed to learn from sequences of graph snapshots over time.
So they look at both the structure and how it changes.
Exactly. They integrate both the structural information from the graph at each time step and the temporal dynamics of how edges appear or disappear. Zhengzheng Chen from the lab highlighted that this integration allows CIGNN to effectively pinpoint anomalies in dynamic systems, making it valuable for proactive threat detection and security systems where it's actually been deployed.
Wow, deployed in real systems, that's significant. One more challenge. What happens when a trained GNN encounters types of nodes it never saw during training? Say, a new type of device connects to your network.
That's the out-of-distribution problem, and it can really hurt reliability. The GNN might make unpredictable or poorly calibrated predictions for these unfamiliar nodes. NEC Labs tackled this with calibration for out-of-distribution nodes.
How do you calibrate for something you haven't seen?
They developed a framework called GRDQ Graph Edge Reweighting via deep Q learning. It uses reinforcement learning concepts, specifically Q learning, to learn how to adjust the importance, the weights, of messages coming from potentially out-of-distribution neighbors.
So it learns to dynamically adapt the message passing when it encounters unfamiliar nodes.
Essentially, yes. It tries to mitigate the negative impact of these novel node types, making the GNN's predictions more reliable and calibrated, even when the graph environment changes.
Okay, so NEC Labs is pushing on robustness, explainability, dynamic graphs, and out-of-distribution handling. That really covers a lot of the practical hurdles. Now, to tie all these architectural ideas, some mean GCN, attention together, can we look at a concrete example, maybe a benchmark data set?
Absolutely. The core dataset is a classic benchmark, perfect for illustrating these differences.
Cora, what is it?
It's a citation network dataset. Each node represents a scientific paper. An edge exists from paper A to paper B if paper A cites paper
Right.
B.
Okay, a network of papers and citations. What's the task?
Each paper comes with some features, typically a bag of words, vector representing the words in the paper's abstract or text. The task is node classification. Predict the research topic, like neural networks, reinforcement learning, probabilistic methods, etc. There are 7 topics in Cora for each paper.
So classify papers based on their content and who they cite or get cited by. What makes Cora interesting for GNNs?
2 things mainly. First, the connections clearly matter. Papers on similar topics tend to cite each other. Second, it's often used in a semi-supervised or low data setting. You might have thousands of papers, nodes, but maybe only labels for a very small fraction, like 20 papers per topic, so just 140 labeled nodes in total for training.
Only 140 training examples for thousands of nodes. That's tiny.
Exactly. It forces the model to rely heavily on the graph structure to propagate information from the few labeled nodes to the many unlabeled ones. You can't possibly succeed just using the node features alone with so little labeled data.
Okay, so what happens if you try? What's the baseline performance using only the paper features, the bag of words, with a standard classifier, like a simple multi-layer perceptron MLP, ignoring the citations?
If you do that, just use the node features, your accuracy is typically pretty low, maybe around 50–55%. It struggles because it doesn't have enough labels and ignores the rich relational information in the citations.
Right, just over chance, basically. So now let's bring in the graph structure. What if we use that simple sum-pulling GNN layer we discussed first? ReLU, A plus I, HW.
Okay, if you build a simple 2-layer GNN using sum polling, the performance jumps significantly. You'd likely see accuracy jump up to around, say, 77.5%.
Big improvement. But you mentioned sum pulling can be unstable. Does that show up?
It can, yes. Depending on the initialization and hyperparameters, sum polling results on Cora can sometimes vary a bit more, reflecting that potential instability from unnormalized feature aggregation.
Okay, so what about mean pulling, where we normalize by node degree, ReLU D1 A plus IHW?
Mean polling generally gives a more stable result and often a slight boost in performance. You might get around 78.5% or maybe close to 79% accuracy. It clearly shows the benefit of that simple normalization for stability and performance.
Better and more reliable. Now, what about the star player, the GCN layer with symmetric normalization, ReLU D12 A plus I D12 HW?
This is where Cora really shines as a benchmark for GCNs. A standard 2-layer GCN model often pushes the accuracy significantly higher, achieving results consistently above 80%, sometimes reaching 81%, or even slightly higher depending on the specific setup and data split.
Wow, so going from mean pulling's 79% to GCN's 81% plus is a noticeable step up, just from changing the normalization scheme.
It is on this benchmark, yes. It really highlighted the empirical effectiveness of that symmetric normalization when the GCN paper came out. It became the number to beat for a while.
What about GAA, the Graph Attention Network? Does learning neighbor importance help further on Cora?
Yes, GAT models also perform very well on Cora, often achieving similar or even slightly better results than GCN, perhaps getting into the 82–83% range sometimes. It shows that allowing the model to learn which citations are more important for classifying a paper's topic can provide an additional edge.
So that Cora example perfectly illustrates the journey. Ignoring the graph gives poor results, 50%. Simple summing helps, 77.5%. Averaging more lane pulling is better and stabler, 79%. Sophisticated normalization like GCN pushes it higher, 81% plus. And learned attention like Geek can potentially refine it even further, 82% plus.
Exactly. It makes the abstract concepts very concrete. The way you leverage the graph structure, especially how you normalize or weight the information flowing between nodes, really matters for performance. It's not just that nodes are connected, but how the GNN processes those connections.
This has been incredibly insightful. We've gone from the basic idea of graphs meeting neural networks through the core mechanism of message passing, explored a whole spectrum of architectures from simple sums to sophisticated attention, seen real-world applications changing industries, touched on cutting-edge research making them more robust and trustworthy, and walked through a concrete example showing how these design choices impact performance.
It really covers a lot of ground. GNNs provide such a powerful lens for looking at interconnected data, moving beyond tables and sequences.
Absolutely. So, thinking about this deep dive, the big takeaway seems to be that connections matter, and GNNs give us the tools to finally learn from them effectively. From finding new medicines, to getting you places faster, to suggesting things you might like, to even securing networks, it's all about understanding relationships.
Well said. The shift towards analyzing relational data is a major trend, and GNNs are at the forefront of it.
So, for everyone listening, the final thought perhaps is this. Start looking for the graphs hidden in plain sight. Think about your own work, your own data, even just your daily life. Where are the hidden networks?
Yeah, customer interactions, process flows, social dynamics, biological pathways.
Exactly. Identifying those relationships, those nodes and edges, could be the first step towards unlocking completely new insights or building entirely new applications using the power of graph neural networks.
This area is moving so fast, too. What we covered is a solid foundation, but there's constant innovation happening. It's a really exciting field to follow or get involved in.
Definitely. Hopefully, this deep dive has given you that foundation and maybe sparked some curiosity to explore GNNs further. It's a complex but incredibly rewarding area of AI.
Agreed.
Thanks for joining us on the deep dive. We'll catch you next time.